In today's lecture, we will be discussing ideal as well as real chains. So, in the previous lecture, we discussed the ideal chain conformations in detail, and the property that defined an ideal chain was that distant regions of that same chain do not interact with each other. So, we will see that we will carry on the discussion on ideal chain a bit further today, and then we will also briefly talk about the behavior of real chains, where in fact the distant regions of the same chain actually can interact with each other, and due to that the conformation and the behavior of real chains are seen to be slightly different from that of ideal chains. So, these are the areas that we will be covering in the lecture today. So, before we begin, we will just go through an overview of the content of today's lecture. So, we will be just summarizing the different models that we covered in the last lecture of ideal chains, and then we will be talking the distribution of the end-to-end distance. So, in the last lecture we discussed the fact that polymer chains can have many different conformations, and the end-to-end distance actually is not a fixed quantity, but it can take many values depending on the different conformations that the polymer chain is adopting. So, we discussed this aspect from a qualitative point of view. Today, we will look at the mathematical function that can be used to describe this distribution of end-to-end distance in a more quantitative way. So, after that, we will briefly look at the topic of radius of gyration of polymer chains, and this quantity radius of gyration actually is another measure of a size of a polymer chain, and it is actually in many cases a better measure than the end-to-end distance, because it can be defined for all the different kinds of polymer chain architectures that are available. So, after discussing radius of gyration, we will also look at next the behavior of real chains, and in particular we will be discussing real chains from the point of view of excluded volume interactions, and the final topic that we will be covering is that of behavior of qualitatively covering is the behavior of these polymer chains in solution, and in particular the concept of theta condition and theta solvent. So, to summarize, in the last lecture we covered four models of ideal polymer chains. So, the simplest model was the freely jointed chain model, where the bond length was fixed, but the bond angle and the torsion angle, these were allowed to have any free value. So, this was the most flexible model among the different models that we studied, the simplest one as well, but of course the least realistic one. We also studied the freely rotating model, where the bond length as well as the bond angles are fixed. So, in most of the real polymers the bond angle are also have fixed values. So, this is a more realistic model, but here again the torsion angles were allowed to have any value. So, in that sense, from that point of view, this model is also highly flexible, because the torsion angle could adopt any values, and we know that it is the different torsion angle values that provide polymer chains or the polymer backbone its flexibility. We also covered the hindered rotation model in the last lecture, where the bond length and bond angles were fixed, but the torsion angle was not fixed free in this case. The torsion angle was allowed to take values based on a certain potential. So, the probability of the occurrence of a certain torsion angle was proportional to a Boltzmann factor, which was an exponential function based on a certain kind of potential energy related to the torsion angles. So, essentially the rotation in this model is hindered due to the presence of a certain potential, and only torsion angles where this potential energy is favorable, or torsion angles which correspond to low energy conformations, those are the ones which are more favored in this model. And we also finally discussed very briefly the rotational isomeric state model, which is the most sophisticated models amongst the ones that we discussed, and which is widely used for predicting conformations of polymer chains. So in this model, the bond length, bond angle again are fixed. The torsion angles cannot take any values, any free value. The torsion angle can only adopt certain discrete values in this case for this model. So as an example, for polymers like polyethylene, there are typically 3 torsion angles which correspond to minimum energy conformations, and usually they are referred to as trans and gauche plus, gauche minus, as discussed in the previous lecture. So this rotational isomeric state model for such a polymer will basically allow only these torsional states, and the entire polymer chain backbone, or the conformation of polymer chain backbone, that can be represented simply as a sequence of these different torsional states. So one such representative sequence is shown here, where we see that torsional states such as trans, gauche plus and gauche minus occur with different probabilities along the chain backbone, and this basically defines the conformation of the polymer chain. So we also discussed about the different mean square end-to-end distances that we obtain by the for these different models. So for the freely jointed model, the mean square end-to-end distance was basically NL square, where N was the number of bonds and L was the length of a bond, and correspondingly the characteristic ratio, or C infinity in this case, is just 1. Similarly, for a freely rotating chain model, again the R square, this mean square end-to-end distance, that is still proportional to NL square, but we have a proportionality constant here, which is a function of the fixed bond angle theta, and in this case the characteristic ratio is defined as 1 plus cos theta by 1 minus cos theta, and this value will be greater than 1. So one thing again to emphasize is that theta is not strictly speaking the bond angle, but it's the angle between the bond vectors, or angle between the adjacent bond vectors. So for the hindered rotation model, again the mean square end-to-end distance depends on NL square, it's proportional to NL square, but the proportionality constant actually has 2 terms, one dependent on the fixed bond angle theta, and another term which depends on an average of the cosine of the torsion angle. So for this case, again one can obtain a value for a characteristic ratio as C infinity. So that basically summarizes our discussion of the different ideal chain models in the previous lecture, and today we will just move ahead and discuss how the chain ends are basically distributed, and how the distribution of chain ends, or the end-to-end distance, how the distribution of that end-to-end distance can be represented mathematically for these simple ideal chain models. So again, if we consider a schematic of a polymer chain as shown here, then the 2 red circles, basically let's say these 2 represent the 2 chain ends, and we have a polymer chain where the bonds are represented by these vectors here, and this dashed vector basically represents that this polymer chain is quite long, and we are only showing a few bond vectors at the beginning and at the end. So for such a representation, the end-to-end vector we are representing by this capital R, this vector capital R. So now our aim is to study the distribution of this end-to-end distance. So the magnitude of the end-to-end vector, that's what the end-to-end distance is, and we wish to study how this end-to-end distance is distributed for different conformations of the polymer chain. The distribution function for this end-to-end distance, let's say that we represent that distribution function by WR. So this function is W, and it's a function of the end-to-end distance R, so we are calling it WR, and this distribution function is basically gives the probability of the magnitude of the end-to-end vector lying between R and R plus delta R. So essentially, if we have an end-to-end vector R, then its magnitude will be given by, let's say, this vector r with mod sign. So let's say this is the magnitude. So this distribution function basically gives a probability that this magnitude will lie between distance r and r plus delta r. So essentially it's the magnitude is close to this value r. So next, if we consider freely jointed chain, it can be shown that this function has the form that is shown here. So the function WR actually has a Gaussian form, okay, where this parameter beta is given by the expression here. So this this function or this Gaussian function basically gives us a distribution of the end-to-end distance. So if we were to plot this WR with as a function of r, okay, so if we let's say plot this function WR as a function of the end-to-end distance r, then it will actually go through a maximum and then again decay at longer r's. The distribution of end-to-end distances has a maximum, shows a maximum, and of course for very large values of r, the probability that two ends are so separated by that large distance, that small. So basically this probability function decays down as the distance r becomes large. This distribution, now that we have this distribution, we must consider its limitations. So the mathematical function that we have shown here, it's not valid for all cases. It's only valid when the number of chain segments or the number of bond vectors, if that is that number is large. So the one condition is that that n, small n, should be very large for this kind of a distribution to be valid, and the other is that the end-to-end distances that we are considering, that should be significantly lower than the maximum stretched length of this polymer, okay, polymer chain. So if we consider again the polymer chain that's shown here, then the maximum length that this polymer chain, if this is a freely jointed polymer chain, then the maximum length again will correspond to this number NL, which is n number of bond vectors times L, the length of a single bond vector. So the end-to-end distance should be smaller than the maximum dimension that this polymer chain can adopt. So only for such conditions this distribution function is valid. Now as we just discussed, this small n is the number of bonds and small l is the length of a bond. This quantity small nl, this quantity is actually has a name, and this quantity is referred to as contour length of a polymer chain. So the contour length of any polymer chain is basically its length as measured by moving along the backbone of that polymer chain. So if one moves along the backbone of the polymer chain, then the length that is measured will come out to be n times L, and that is referred to as the contour length. So basically the condition for validity of the end-to-end distribution function is that the end-to-end distances that are being described should be significantly lower than the contour length of the polymer chain. The reason for this limitation is that the Gaussian function that we have considered here, if we take a close look at it, even for values of r, even for values of this end-to-end distance r greater than nl, even for these such values, the distribution function actually does not decay to 0. It has a very small but a finite value. But physically speaking, this any end-to-end distance greater than nl is physically not possible. It's an unphysical scenario. So but the mathematical function that we have, it gives a non-zero probability for the occurrence of such end-to-end distances as well, r greater than nl. So so that's why this functional form is basically valid only for r or end-to-end distances smaller than the maximum stretch length of your polymer chain. for values of r equal to greater than NL, this does not describe the correct behavior because it will predict non-zero probability for occurrence of such end-to-end distances as well, which is completely unphysical. So this is the discussion that that applies to a freely jointed chain. Now let's consider the case of not a freely jointed chain but any ideal chain. So for any ideal chain, it can be any chain which where the interaction between distant regions of the same chain are not present. That's the definition of ideal chain. So for any such ideal chain which is not necessarily freely jointed, it can be freely rotating. It might be something that is described by the rotational isospheric state model. So for any such ideal chain, one can actually rewrite the same distribution function for the end-to-end distance WR. So that same equation or expression is valid. The only thing is that the parameter beta that we had described earlier, the definition of beta changes. So if we look at this expression for beta here, instead of the small n we have a capital N here, and instead of L square we have B square here. So if you remember from the previous lecture, we had defined these quantities capital N and the small b as the number of segments, number of bonds, and the bond length for an equivalent freely jointed chain. So any ideal chain can be represented or can be mapped using an equivalent freely jointed chain, so that this equivalent chain that we have mapped onto it, that behaves like a freely jointed chain. So this capital N and B basically are the number of bonds and the bond length for the equivalent freely jointed chain for our ideal chain here. So again, the validity in this case also applies only when the end-to-end distance that we are considering is much smaller than capital N times B, which is again the contour length for this equivalent freely jointed chain corresponding to any ideal chain that we have, and also the number of such bonds should be quite large. So as we discussed, the capital N is the number of equivalent bonds, or also referred to as Kuhn monomers, and this we discussed in the last lecture, and B is the length of this equivalent bond, and it's also can be written as, or it's also known as the Kuhn length, and this is also something that we discussed in the previous class when talking about the equivalent freely jointed chain. So again, as discussed, the magnitude of the end-to-end vector should be much smaller than the contour length of our whatever ideal chain that we have. So if we consider this distribution function, if we want to find out the mean square end-to-end distance using this distribution function, that is possible, and that can be done by simply integrating r square multiplied by this distribution function WR times dr and integrating from 0 to infinity. So this basically is what's called the second moment of this distribution function, and this second moment of this distribution function gives us the mean square displacement. So for an ideal chain or a freely jointed chain, let's say, if we substitute the expression for WR here, which is given here, so if we substitute this expression here in this equation, then for a freely jointed chain, the mean square end-to-end distance that is given by this integral, and upon integration it can be shown that this integral comes out to be just NL square, which is a result for a freely jointed chain that we discussed in the previous lecture. So to basically carry out this integration, one can use the standard mathematical integration formula, x to the power 4 exponential of minus ax square dx integration of 0 to infinity, that's 3 by 8 square root of pi a to the power minus 5 by 2. So if we use this relation, and in here if we use this parameter a as beta square, then we can use this relation to integrate this expression here and prove that the mean square end-to-end distance is equal to NL square in this case as well. So this distribution function that we have discussed as it's applicable to any ideal chain, provided that we are using the cone length and the number of cone monomers, and for a regular freely jointed chain, of course, it's applicable as well. So next, let's discuss another important quantity for describing or characterizing the size of a polymer chain, and that quantity is referred to as the radius of gyration. So this radius of gyration, this quantity actually is quite useful because it's something which can be defined for any kind of polymer architecture. So if we consider the mean square end-to-end distance, the measure of size that we have been using till now, so that mean square end-to-end distance actually using it is problematic for certain polymer chain architectures like a cyclic or a ring polymer. So for a cyclic polymer, there are no chain ends, so the mean square end-to-end distance basically is 0 for that case. So again, that's a problem, that in that case the mean square end-to-end distance does not give us any information about the size of a cyclic polymer. Similarly, if we have a branched polymer, so for a branched polymer, again there are many chain ends. There are not just two chain ends, there are multiple chain ends in a branched polymer. So again, there if we can try to calculate the mean square end-to-end displacement, the quantity itself is not well defined because we have many chain ends and not just two chain ends. So what we notice is that mean square end-to-end distance is a good measure of size of linear polymer chains, but when we consider other kind of polymer chain architectures like branched polymers or cyclic polymers, then the mean square end-to-end distance itself fails to describe the size of such polymer chain architectures. So radius of gyration, as we'll see, is actually useful measure of the size of polymers of any architecture, and the reason for this is the radius of gyration basically is defined in a way such that it's possible to define it for any kind of polymer chain architecture. So the equation defining the radius or the square of the radius of gyration is shown here, and the square of the radius of gyration is defined as 1 over n summation over all the let's say monomer units present in your polymer chain. So summation over all of that, and the summation is carried on the quantity Ri minus Rcm square. So this Ri and Rcm are basically what's called position vectors, okay, and the Rcm here is the position vector of the center of mass of your polymer chain, and Ri is the position vector of the individual monomer units on the polymer chain. So the Rcm, or the center of mass, position vector of the center of mass, can simply be represented as an average of all the position vectors of all the monomer units present in the polymer chain. So let's say if we again draw a simple schematic of a polymer chain like this, and let's say our coordinate system is such that the origin is located somewhere here, and we have our, let's say, x, y and z axis like this. So let's say that this monomeric unit, let's denote it as monomer unit number I. So if we draw a vector from the origin to this monomeric unit, that's what this position vector Ri represents. So the Ri in this formula here is the position vector of any ith monomer unit on your polymer chain from the origin of the coordinate system that we have chosen. This in this summation here, the I runs from 1 to n. So basically we will be considering the position vector of each monomer unit in the polymer chain. Now the Rcm, or the position vector of our center of mass of the polymer chain. So if we let's say that this is a point which represents the center of mass Cm, or the Cm stands for center of mass. The Cm, or center of mass, of this polymer chain is at a certain point located here. So now the position vector, or the vector connecting the origin to this point, the center of mass, that's what this vector Rcm is. So this RCM is the position vector of the center of mass, and as we discussed, if we know the positions of all the monomer units present, then just the average of those vectors, or just taking the vectors, sum of all the position vectors of the monomer units and dividing that by the number n, that will give the position vector of the center of mass. So if we combine these two, combine these two relations, and of course carry out some mathematical steps, then what can be shown is that the radius of gyration square can be represented using the formula here. So in this formula we see that there is a double summation over both I and j. So for any two monomer units, let us say I and j, this Ri minus Rj basically represents the vector between these two monomer units, and the square of that, and again double summation of that, if we perform that step and then divide by n square, that will also give you Rg square. That's what this formula tells us. So if we let us say have a polymer chain and the location of all the monomer units are known, then instead of separately carrying out a calculation of the center of mass and using this first formula here, instead of doing that, we can directly use this second formula here, since we already have the positions of all the monomer units known in the polymer chain. So next let us talk about the mean square radius of gyration. So as we discussed in the last lecture, the polymer chain ends basically, or the distance between polymer chain ends is not fixed, it keeps on changing, and the reason for that is the polymer can adopt many different conformations because of its backbone flexibility. So depending on the vast number of different conformations that are possible, one can have a vast number of end-to-end distances possible, and that's why we chose a mean square end-to-end distance to represent the polymer size. So same is true for the radius of gyration as well. So these equations that we have defined here, these are valid only when we are considering a single polymer chain conformation. But as we know, the polymers have flexible backbones and they can adopt a huge number of conformations. So again, the radius of gyration also cannot be uniquely defined, because for each of the different conformations, the radius of gyration actually will be different. So different conformations will correspond to different positions of the monomer units, which will lead to different values of radius of gyration. So for these reasons, instead of using a unique radius of gyration value, a mean square radius of gyration value is also employed. So the mean square radius of gyration, again represented by the angle brackets, which as we have discussed before, represents the ensemble average. So this mean square radius of gyration, that again is simply can be defined in using either of these two relations. So in both these cases, the angle brackets represent the ensemble average of these quantities, which means the average over all the different polymer chain conformations that are possible. So next, for an ideal linear chain, okay. So the equations that we have discussed till now for radius of gyration or the mean square radius of gyration, those equations are valid for any kind of polymer chain. So for any kind of chain molecule, those equations are mathematical definitions of the radius of gyration, and they are strictly valid. The only assumption in all those equations is that all the monomer units have the same mass. If the monomer units are of different masses, then the individual mass of the monomer units also has to be accounted for, and the equations that we have here, these equations actually will not be directly applicable. One will have to modify them to include the different monomer masses. But if we have any linear polymer chain, and if all the monomer units are of the same type, which means they will have the same molar mass, so in that case those equations are valid. Now if we consider the special case when the polymer chains are ideal polymer chains, so in that case one can actually show, will not go through the derivation of the proof here, but it can be shown that for an ideal linear polymer chain, the mean square radius of gyration is basically given by nb square by 6, which is also again equal to the mean square end-to-end distance by 6. So again here the capital N and the small b represent the number of bonds and the bond length of the equivalent freely jointed chain. So capital N is basically the number of Kuhn monomers and small b is the Kuhn length of the equivalent freely jointed chain corresponding to any ideal chain that we are considering. So if we consider just a simple freely jointed chain, so in that case mean square end radius of gyration can simply be written as NL square by 6. So we see that the radius of gyration for ideal polymer chains, that in magnitude it is smaller than the mean square end-to-end distance. So later on we will also again encounter radius gyration when we talk about measurement of polymer molar mass, and we will see that this is a property that can be measured experimentally. So that is another advantage of using radius of gyration to describe polymer chain dimensions, because apart from the fact that it can be defined for any chain architecture, it is also something that is experimentally measurable. So till now we have been talking about ideal chains and the different models of ideal chains and so on. Next let us spend a little bit of time on real chains. So we know that ideal chains are chains and basically an idealized concept where the polymer chain is such that even the distant parts of a polymer chain distant parts of the polymer chain do not interact with each other. Okay, so if there are two monomers which are located far apart along the polymer chain, then they can come very close in space and then still they are not interacting. That is what an ideal chain model implies. So if let's say if we have a polymer chain like this, one of the conformations can be like this. If we are considering an ideal chain, then basically a conformation where part of the polymer chain basically intersects with another part, that is allowed. Okay, so physically speaking, that is something that will not happen. The same physical region of space cannot be occupied by two different monomers on the same polymer chain. So physically that is not a very realistic kind of model, but that is what the fundamental assumption for an ideal chain model is. So in a real chain basically such interactions are allowed. So a real chain is of course a chain where polymer segments or monomeric units on a polymer chain, even those which are separated by long distances along the polymer backbone, if they are close enough to each other in space, then they will interact, and different parts of a polymer chain cannot overlap with each other. So basically for real chains what happens is that if you are considering till now all the models and everything that we have discussed is for isolated polymer chains. So for if we have a single isolated polymer chain, how does it behave? So for an isolated polymer chain, in real chains, any and each part of the isolated polymer chain molecule can actually interact with other parts of the same molecule, because each part actually excludes other parts of the same chain from the volume that it is occupying. So if a certain part of a certain monomeric unit in its real chain is occupying a certain physical volume of space, then if we are considering some other monomeric unit in the same chain which is some distance away along the polymer backbone, then that other monomeric unit cannot occupy the same physical region of space as being occupied by this monomer. Parts of the polymer chain basically exclude the other parts from the volume that they are occupying, and that is something that physically reasonable as well. So what happens because of this fact that in real chains parts of chains exclude other parts from the volume that they are occupying, the mean square end-to-end distance in a real chain basically turns out to be larger than those in ideal chains, and this is because of what is called the excluded volume interactions. So as we discuss, excluded volume interactions are interactions which result from the fact that a certain part of a given polymer chain excludes other parts of the same chain from the volume that it is occupying. So such interactions are called excluded volume interactions. And in an ideal polymer chain, such interactions are not present. So distant parts of the polymer chains can overlap, and such conformations are allowed. In a real chain, if distant parts of a polymer chain of the same polymer chain are overlapping with each other, then such conformations will not be allowed. And due to excluded volume repulsion, basically the dimension that a real polymer chain adopts, that those dimensions tend to be higher or larger than the size that ideal polymer chain adopts. So the real polymer chains, because of these excluded volume interactions, are larger than the corresponding ideal chain. So the relation between these the dimensions of these real polymer chains and the ideal polymer chains, that relation is shown here, and in this relation the parameter alpha r, is referred to the expansion parameter, and this basically is a measure of how much larger the real polymer chain is compared to the ideal polymer chain size. So the subscript 0 here, that basically denotes what's called the unperturbed dimension, or the dimensions in the absence of excluded volume interactions. So these unperturbed dimensions are basically dimensions of an ideal polymer chain, and if we apply this expansion factor alpha r to the dimensions of ideal polymer chain, then we will get the dimension of a real polymer chain. So let's say if we consider a freely jointed FJC or a freely jointed chain model, if we consider an example of that, then in such a model, this the unperturbed dimension, or r square naught, is just NL square. So this is just the ideal chain dimension. So in this case, the what's called the dimension of the real chain, that will correspond to alpha r square root of n times L, because we are in this relation the r naught square root of r naught is considered here in the definition of alpha r. So so basically, if we have an idea about the dimension of an ideal chain, and if we know what the expansion parameter is, or if we can relate the expansion parameter to some things which are known. So if we have these information, then based on this, the dimension of the real polymer chain can be predicted directly using the relation that's shown here. So we know that for ideal polymer chains, this mean square end-to-end distance basically scales as n, or the number of bond vectors present in the polymer chain. So for a real polymer chain, there should be a half here actually. So for a real polymer chain, the square root of this mean square end-to-end distance, or square root of this r square, that actually is proportional to n to the power 3 by 5 or n to the power 0.6 for if the chain is expanded due to excluded volume repulsions. So in that case, this the end-to-end distance basically scales as n to the power 0.6 or 3 by 5. So if we consider ideal polymer chains, then this scaling for, let's say, ideal polymer chains, this scaling is or this proportionality is to square root of n, which is n to the power 0.5. So we see that as a number of monomer units or segments in the chain increase, then the rate at which the size or the end-to-end distance of a polymer chain increase, that rate is higher for a real polymer chain compared to the ideal polymer chain, because in ideal polymer chain it scales as n to the power 0.5, whereas for a real polymer chain, the square root of the mean square end-to-end distance, that scales as n to the power 0.6 or n to the power 3 by 5. Finally, let's talk a little bit about, before concluding, let's talk a little bit about the behavior of real chains in the presence of other substances, like if the polymer chain is in a solution, so it will be surrounded by solvent molecules, or if the polymer chain is not isolated, but if it's in the presence of or if it's surrounded by other polymer chains of its own kind, like in the case of an amorphous polymer sample or a polymer melt. So in such cases, how the behavior will be. So specifically for now we will focus on the behavior of real chains in solution. As we have just discussed, the real chains have a larger dimension than ideal chains, and these perturbations from ideal chain dimensions result from excluded volume interactions. So basically different parts of the polymer segment cannot overlap, and they if they come close to each other, there's excluded volume repulsion, and that's why overall the size of the real polymer chain is expanded or larger compared to the size of an ideal polymer chain, which is the unperturbed dimension. So we discussed in the previous slide that there's an expansion parameter alpha which can be used to relate the real polymer chain dimension to the ideal polymer chain dimension, and this expansion parameter actually in the last slide we discussed the case of an isolated polymer chain, but even if a polymer chain is present in a solution where it's surrounded by other solvent molecules, even in such cases this expansion parameter takes care of the effect of the surrounding molecular environment. So that such details are actually incorporated in this expansion parameter. So let's consider the behavior of dilute solutions. We are focusing specifically on dilute solutions for now, because in a dilute solution the polymer chains themselves will not interact with each other. Different polymer chains will not interact with each other. If the polymer solution is dilute, the chains will basically remain isolated from each other, and each chain will be separately surrounded by solvent molecules. So in such dilute polymer solutions where the chains are not overlapping, different chains are not overlapping with each other or not getting entangled with each other, and where the chains are essentially isolated from each other, there the primary interactions that are of interest are the excluded volume interactions that are internal to individual isolated chains, and the interaction between the solvent molecules and the monomeric units or the segments of the polymer. So what will happen is that if we have a polymer chain present in such a dilute solution, then excluded volume interactions will want to expand the polymer chain dimension from its ideal dimension. So the segment repulsion will want the polymer chain to swell. Now if the polymer because the solvent is also present around it, depending on the nature of the interaction of this polymer chain with the solvent, the actual behavior of the polymer chain will be dictated by both these interactions. So the internal interactions between segment due to excluded volume interactions, and the segment solvent interactions, both of these will govern how the polymer chain basically, what kind of dimensions they adopt in solution. So if we have a good solution, so will be doing a very qualitative discussion here. So if we consider a good solution is where the polymer segments basically have favorable interaction with the solvent molecules. So what said is that the polymer segments like the solvent molecules, and in that case internally the segment repulsion due to excluded volume interactions, that will try to expand the polymer chain, and since the polymer is having favorable interaction with the solvent molecules, it does not have much problems with expanding. So polymer will adopt an expanded conformation with alpha or the expansion parameter value larger than 1. So for in the presence of a good solvent, the polymer will swell and it will adopt an expanded conformation where its size will be larger or significantly larger depending on how good the solvent is. It will be larger than the unperturbed or the ideal chain dimension. Next, if we consider the other extreme where the solvent is poor and where the polymer segments basically are not interacting favorably with the solvent molecules. So if the polymer segment and the interaction with the solvent is poor or unfavorable, in that case what will happen is that internally again the segment repulsion will be such that the polymer will try to adopt an expanded conformation, but because the polymer chains themselves are interacting poorly or unfavorably with the surrounding solvent molecules, that other effect basically will shrink the size of the polymer chain. So, essentially in a poor solvent where the solvent segment interactions are unfavorable, the polymer chain will not adopt any expanded conformation, it will adopt a contracted or a shrunk kind of conformation. And in fact, if the solvent quality is very poor, so that the interaction is very unfavorable between the polymer and the solvent, then in such cases the solvent essentially becomes a non-solvent such that the polymer chains basically precipitate out of that solution. So, in the case of a poor solvent, if we have a condition where the segment repulsion due to excluded volume interaction of the polymer chain, if that repulsion is counteracted and counterbalanced by the solvent segment unfavorable interactions, if these two effects are exactly balancing each other, then basically we have a situation where the polymer chain adopts nearly ideal conformation, ideal chain conformation or ideal chain dimensions. So, such a situation or such a condition is referred to as a theta condition, and the solvent for which such condition arises, such solvents are called theta solvent. So, in a theta solvent, what we have is that the internal polymer segment repulsion due to excluded volume, they are balanced by the solvent segment repulsion. So, these two interactions which are working in opposite direction balance each other in such a way that the size of the these are real polymer chains, but because of the balance of these two interactions, the size of these real polymer chains basically correspond to the dimension of ideal polymer chains. So, for theta solvents or theta condition, the real polymer chains are also known to adopt ideal chain dimensions, and this is something that has been observed it's not just some theoretical argument, it's observed experimentally as well. So, what we see is that if certain conditions are met, which is true for a theta solvent, then the real polymer chains can also assume unperturbed dimensions. And this concept of theta solvent is something that we have introduced here in a very qualitative way, but in the next few lectures, when we will talking about polymer thermodynamics, we will be discussing this concept of theta solvent in a bit more detail. So, with regards to the conformations of ideal polymer chains and behavior of real chains, qualitative behavior of real chains, this is where we will conclude our discussion. So, what we have learnt is that the ideal polymer chains can be described by different kinds of models of different complexity, and basically if we have a real polymer chain, then in that case the dimensions typically are expanded compared to an ideal polymer chain because of excluded volume interactions. But when we can have certain conditions where real chains also adopt ideal chain dimensions. One such condition is where the solvent is of such a type that the segment internal repulsion of a real chain is counterbalanced by the solvent segment repulsion, and such a solvent is called theta solvent. So, that is one example. Another example is where basically is the case of amorphous polymer chain, polymer samples or polymer melts, where from the perspective of polymer chain, again the polymer chain will want to expand due to the internal segment repulsions, again due to excluded volume interactions, but because it is surrounded by other chains as well, the segments of the given chain will also interact with the segments of the surrounding chains, and those segment repulsions will again counteract the internal excluded volume interactions. And again in such cases where we have a very concentrated collection of polymers, multiple polymer chains, the internal repulsion excluded volume repulsions within the chain are counterbalanced by the external repulsions between different chains. And again in such cases also it has been observed that ideal polymer chains dimensions are assumed. So, that basically concludes our discussion of polymer chain conformations, ideal polymer chain models, and qualitative behavior of real chains. In the next lectures we will be focusing on the thermodynamics of polymer solutions in more detail.